Welcome to Module 4 Input-Output Analysis, where we talk about modeling the future. So far we assumed that input-output tables are static, which they are in nature. But quite often in economic planning or impact analysis, we also want to look into the future and not just see what is the impact today, but also want to analyze the impact of policies and planning stuff for the future. So we therefore have to create input-output tables which are either dynamic or in the future. And by that, we have to differ between two concepts. We can either forecast the future or we can create dynamic input-output models. In forecasting, we have future relationships that are still static, so we forecast single periods. And we do this either by extrapolation or econometric methods, and we still have this static relationship that we have in input-output tables, and it's mostly used for short or medium-term things. So saying this forecasting aspect is pretty much a guessing game. An educated guessing game, but still it is a guessing game. And it's an explicit guessing game. You have to state what you guess. Dynamic is a little bit different. Here you have evolution of relationship between sectors. You have mostly multi-period models that are where the timeline, so different years, are interconnected with each other. And you apply an intertemporal optimization, you have feedback loops, you can have capital accumulation, and you have learning mechanisms which change the model from year to year. And that's why those models are more used for medium and long-term analysis. So this evolution sounds like a really natural thing, and compared to the educated guessing game, well, it still happens here, the guessing. But it's more implicit because you guess how things can evolve, what are the relationships. So it's quite often used to also hide assumptions. So if you ever make a dynamic input-output model, I would really appreciate if you state clearly what your assumptions are. Like always in economics, state the assumptions so it's easier to believe you and to follow through with what you have done. I want to start with a few methods, give you an overview how those forecasting and dynamicization of an input-output table can look like. It's just a starting point, so in case you want to dig deeper into that, I really recommend looking into books here. Miller and Blair have a brilliant part of the book where they talk about forecasting and dynamicization of input-output models. Or Henry Tail as well, famous for the Tail index, has also done really great work in the 60s on that. On forecasting, I mentioned already the word of extrapolation. In extrapolation, we forecast sectoral output and final demand that will be observed in the next year and the year after. And we apply an ARS algorithm to smooth and balance out the input-output table in its intersectoral dependencies. If we apply econometric modeling, we normally look more at the technical coefficient matrix A, and we run a regression on how the specific factors changed over the previous years. And what we assume is that the same change that we have observed over the last year will be also observed in the future years. So we have a time series model for the technical coefficient matrix or the final output, and therefore can forecast the input-output table for the future years. There's also the possibility to apply machine learning. And machine learning, as often as it is used as a buzzword recently, it is nothing else than predicting the future based on the past. Quite often it's a black box that uses correlation factors, and different machine learning algorithms will apply that in different ways. So here as well, don't just throw the keyword, oh, I applied machine learning. Be transparent and tell us what you've done, how you've done it, and why you've done it. To summarize forecasting things, we assume mostly fixed relationships in the production process. We have really, really slow adjustments over time. We have barely any shift in capital. So what you will not see by forecasting, because it's technically impossible, that you have major shifts in the economy. So it is not possible to have all the production capital shifting from the automobile sector into renewable energy, because the capital is bound. Those big shifts are not able to be captured. And I put in here this famous quote of John Maynard Keynes that in the long run we are all dead. So what does it matter to forecast the economy? Because there's so much uncertainty and unpredictability, it's really difficult to have that incorporated into your model. Dynamic modeling is a little bit different. The basic dynamic model is, of course, where future production really depends on current production and current demand. So you have here that future production includes the investment and capital stocks that you have today, and therefore you build on today's economy to produce tomorrow. You can also really easily include resource and environmental limits here with a basic dynamic model. You say like there are specific limitations on resources that can be reused in the following year. The same as if you apply intertemporal optimization. There you have a trade-off between current and future output. So what you see there is you have a limit on output. I mentioned that before, that we live on a planet with limited resources. So all the resources we use today cannot be used tomorrow, as long as we're not going circular, of course. So what we see here is that you have a limit in availability of oil, for example. So all the oil we use today cannot be used tomorrow, and therefore we might have a huge economic positive aspect today, but we will see an economic dampening tomorrow when all the oil is used. So intertemporal optimization would allow you to stretch the use of oil over the next decade and therefore have a more tempered economic development. We also see quite often computable general equilibrium models. They are extremely messy from a mathematical perspective. That's nothing you want to solve by hand. This is something your computer will take a few minutes to calculate through. Because suddenly we can incorporate prices and substitution of goods. So you shock a sector, price adjustment happens, substitution effects happen, everything might even happen at the same time. Things might run through faster than other things through the economy. And so with the feedback through prices, you have impact on supply and demand in the next year, in the current year. You can incorporate expectations and, oh, I assume price changes in the future, so I will consume today. And all those things can be incorporated into computational general equilibrium models. And to summarize that, dynamic models have relationships which evolve over time. Here we definitely have the possibility that capital can shift based on pricing, based on substitution developments, based on assumptions you throw into the model. For example, capital has to shift out of the oil industry if we run out of oil. So environmental limits lead to capital shifts. And also structural shifts can be incorporated, like we suddenly produce every energy as renewable energies. All those things can be incorporated and taken into account for a dynamic modeling of input-output tables. I hope this gave you a nice overview of what is possible, and depending on the problem you're looking at, you might want to take one or two of those approaches, look deeper into them, and see how they play out. For a seminar paper, probably, a forecasting aspect is quite easy to comprehend, to apply that to your model. Dynamic modeling is more a thing for a master thesis or even a dissertation if you want to provide your own dynamic model. If you want to use one, don't worry, they are out there. Someone has written them, someone provided the code, and most of them are really good for sale because it's a lot of work, so they want to get some money out of that.